to hear what folks are interested in hearing about, and you know, we want to know what you want to know.
So I had one email from someone that watched the astrology and astronomy section, and they asked me about, they had seen a reference to a Doc Savage novel where Jupiter was ascendant. I think, isn't there a movie called Jupiter Ascending? Anyway, we didn't cover ascendants in the talk, and all it means is rising.
Like rising over time, or rising?
Or like rising in the east. So if when the person was born, Venus was ascendant, it just means Venus was rising in the east at the time.
Right. Okay. So
you can cut and splice this piece and put it in the middle.
We're just continuing on from last week. Hey, everybody, a reminder to those of you who are in the Zoom chat, thank you for sharing where you're joining from. I'm sorry that Horseshoe Bay is rainy today. It's been cloudy here, although we did have a very short period of clear skies over the past couple days.
I saw the moon this morning on my walk.
Me too. It was beautiful, eh? It was so bright. Oh, yeah. Anyway, winter really makes you appreciate the clear skies. So just a reminder to those in the chat, if you're interested in talking to everybody, make sure to change that little blue bar from panelists to all panelists and attendees so that you can talk to everyone and not just Chris and I. Sorry for the confusion last week. I know some people thought there was a session. We only do sessions every 2 weeks. So the next session after this will be February 16th. And so there's a little week break in the middle. And I'm pretty sure I didn't change the email again that I sent for a reminder, and I'm pretty sure it says something about astrology in it, so I apologize. Today, we're not talking about astrology, although we kicked it off that way. Today, we're talking about traveling through time, which is equally fun and exciting. Yes. Chris is going to take us on a tour of time travel-y targets, and we're going to take a look at some distant objects in space today.
Yeah, so first of all, happy Groundhog Day, everybody.
Yeah.
First of all, happy Groundhog Day, everybody. See what I did there?
Oh my God.
We could talk about what Groundhog Day, the significance of it when we do our future session on celebrations linked to astronomy. So first of all, as everybody knows, space is huge. It's vast, right? It's big. And so when we want to figure out where things are, how far away they are, meager human-sized rulers and measuring units just don't cut it. So astronomers have developed other nomenclature and other units to be able to more manageably express the distances between objects in the sky. And that's where we get expressions like astronomical units and light years and parsecs and even redshift values that you may have come across. So I'm going to actually run through what all of those kind of mean and how they come from. Like parsecs, you've heard the name parsecs if you're a Star Wars fan, right? Because Han Solo said he made the Kessel Run in less than 12 parsecs. But parsecs is the distance, it's not a time. So we'll break that down for everybody as we go here. The basics for all this is the fact that the speed of light in vacuum is the fastest speed limit for the universe. It's the fastest things can go. And for anybody that hasn't already have it memorized, it's 299,792,458 meters per second.
3.0 times 10 to the 8 meters per second.
Yeah,
right?
It's a billion kilometers an hour.
Speedy.
Yeah, 1.08 billion kilometers an hour. It's easier to remember that way. And so any time interval that you pick, you can figure out how far light would travel in that interval of time. So for example, in 1 second, light would travel 299,792.5 kilometers. Right, which is still pretty far. The moon is about 385,000 kilometers from the Earth. And so it takes the light from the moon 1.28 or so seconds to get here. And would call that a 1.28 light seconds, that distance. If you want to use that, that's not that helpful. I mean, moon's still close enough that kilometers works.
It is neat though, because I know at the Science Center for a while, at the Ontario Science Center, they had an exhibit where you could see yourself as if you were on the moon. So with that 1.2 times 2 for the time it takes to get there and back delay. So you can, it's a nice visualization because it's a time scale that we're used to.
Yeah. And we'll get into a little more of the extremes of that in a minute. I'm just going to set a little more of the stage here. So that's a light second. A light minute would be, let's see, a light minute is 17.99 million kilometers. And so using that scale, the sun, the distance of the sun from the Earth represents 8.317 minutes of light travel time. And that's what we call an astronomical unit. So it's about 149.6 million kilometers as the mean distance from the sun to the Earth. And for shorthand, we call that an astronomical unit in astronomy. And it's a perfect unit for dealing with planetary distances, right? Because all the solar system planets are at some multiple of that without getting too crazy. I think Pluto is on the order of 29 or 30 astronomical units away from the sun. So it's 30 times as far from the sun as we are. So that's handy.
I like astronomical units as a unit because it feels more like a distance than something like light minutes or light hours, because light minutes and light hours have units of time in the total name of the units. It can get kind of confusing.
Yeah. Well, yeah, it's a matter of what you're used to working with, right? So that's light second, that's light minute. Of course, you can do light hour. So a light hour is, because I already gave it away. I already said that the speed of light is 1.08 billion kilometers an hour. So a light hour is 1.08 billion kilometers.
True.
Easy. And then light year. So light year is the one that's most useful for interstellar distances. And we even use it for extragalactic measurements, right? To the distances to other galaxies. And so a 1 light year is 9.46 trillion kilometers, or about 10 trillion kilometers. And that's what we can use. We can first really start using it when we get to the edge of our sun's neighborhood. The sun is enveloped by a vast cloud of icy bodies called the Oort cloud. And it's getting to the 1 light year distance from the sun, which is why if other stars pass not too far from our sun, they can gravitationally jostle those distant objects and create the comets that fall into the sun. So to make all this work though, the farther away something is, the more difficult it is to measure how far away it is, because you can't just get out a ruler and measure it. So watch, what we have is something called the cosmological distance ladder. And they're like steps on a ladder where you start at the bottom with things that you can measure directly. And then once you know where they are, if you can find those objects in another farther distant location, you can perhaps infer how far away they must be in another thing. And an example of that would be a certain kind of star in our Milky Way. We know how far away that star is, and we see that same type of star in another galaxy, then we can maybe figure out how far the galaxy is, and we'll get into a bit of that. So it's called the cosmic distance ladder, and it goes all the way from, just our local neighborhood right out to the farthest galaxy and towards the beginning of time after the Big Bang, really. So let's start close to home. So how can we measure distances of things close to home? Well, one of the easiest things to do is to use ranging, where you bounce light or you bounce radio off an object, and the travel time there and back at the speed of light gives you its distance. Just like, you can do that for planes orbiting the airport, that kind of thing. They can tell how far away the planes are and even what direction they're in. So interestingly enough, the Apollo missions left reflectors on the moon's surface that we can send laser beams to the moon and reflect back. And there was an episode of Big Bang where they were playing with that, I remember.
They're really cool because there are 3 mirrors as if they're set up in the corner of a square. And so no matter which way the light comes in, it bounces directly backwards, which is how the lasers, like you can point lasers from anywhere on Earth and the light still comes straight back, which is really, really cool.
It's the same, it's exactly the same structure that you use in car taillights, the reflecting part. There's three, if you look at them closely, you've got the three little
You're right.
corners of squares, corners of squares, corners of squares, all in a lattice, and it gives you that retroreflection.
I had never made that connection. That's very cool.
Same principle. So yeah, so the Apollo missions let us range from the surface of the Earth to the surface of the Moon, to where that retroreflector is. You can also, but it gets harder when things are far away, because we like to switch to use radio, because radio, we can produce dishes that act as giant ears to listen for the radio signal coming back. So we've bounced radio signals off of the Moon. What have we got here? Notes. Let's see. Yeah, 1946, we sent the first radar out to the Moon and back. And then we did it for Venus in 1961, in the early days of radar. Then we started using the Arecibo radio telescope. That's the one that collapsed back in December, I guess it was, late last year. And it was not only a receiver, but it was a transmitter. So it would transmit radar beams out to asteroids that were near Earth asteroids that might be coming close to the vicinity of the Earth and the Moon, in order to exactly measure where they are in space and their trajectory, and whether and determine their orbits very accurately. And also to map their shape, because by continuously pulsing off a rotating object, you can build up a three-dimensional representation of its shape. So Arecibo, as the records I saw, had already radar ranged about 20 comets and 1,000 asteroids. And it's a loss to lose that observatory, and I guess the hope is that they'll rebuild it soon.
Yeah, it is
now
sad.
When you send a signal out, the signal actually spreads out as it leaves your transmitter, and it actually goes as the square of the distance away. So the signal drops off as the square of the distance away. And so by the time the radar gets to the Moon or gets to the asteroid or whatever it is, it's gotten fairly weak. And then that reflection coming back in our direction, it's also dissipating as the square of the distance and the return back. So it's really 1 over r to the 4th is the power. So radar actually becomes really weak for farther away objects. I think Saturn is about as far as we've been able to practically do from Earth. So that gives us a limit on where we can use radar and lasers. Yeah.
Can I jump in quickly before you continue on to the next one? I just wanted to, when we're talking about time travel, it has a lot to do with the speed of light. That's why we're also talking about these units of measurement with the speed of light, because mostly I want to make this connection very, very obvious, because if you're looking at an object like the sun, and I'm sure many of you have heard this before, we're seeing it, the light from the sun takes 8.3 minutes to get here. So what we're seeing, the light that we're seeing with our eyeballs is 8.3 minutes old. And so we're seeing the sun 8.3 minutes ago. We're looking back in time.
Yeah.
And that's the case with everything in the sky, almost everything. Technically, it's the case with everything right now. It's just that the time period is very, very, very short. So when we look at things like Pluto in the sky, that's hours away. Light hours away.
We'll sort of get into a list of objects moving out from distance, but basically your environment around you, you're seeing delayed by 3 nanoseconds per meter away from you.
Right.
Yeah. So if you're talking to a person
close by or really fast,
happening in the past. Yeah.
So I just wanted to make that connection very clear that by time traveling, we're talking about looking at things in the past.
Yeah, because of the light that we use as astronomers and stargazers is taking all that time to get to us.
Old light. And
so the farther away something is, the farther in the past its light is coming. It's the farther in the past we're seeing it as. And that's the whole basis of this traveling through time idea. So once we get past measuring distances using radar ranging or light ranging, the other thing we get to using is geometrical parallax measurements. Now everybody can do this. If you put your finger out in front of your face and alternate eyes, your finger will hop left and right. And if your finger is close to your face, the amount it hops is very big. And if your finger is at arm's length, the amount it hops is less. And what you can do is you could actually measure the angle or the distance that your finger hops and do math to figure out how far away your finger is from your eyes.
That's
So,
cool.
yeah, so surveyors use it. Those things you use on the golf course to figure out how far away the golf hole is, they sort of use this sort of trigonometric idea of measuring the angles to figure that out. So that's called parallax. The idea that an object, now when you're using alternate eyes, it's as if you're stepping left and right by the eye separation. So we're just doing it with using two receivers.
Right, it's like going from here to here with the same eye.
Yeah.
If you wanted.
But you could also look at something in one position and you could step to the left or the right and look again, and you'll see compared to the objects way in the distance, it'll have moved. And the closer it is to you, the more it moves compared to those distant objects. And so that works with stars. The farthest away stars that we can see would not seem to move at all, regardless of our position. But the stars that are nearby will appear to move in the sky if we move our location. And so are we moving our location when we're looking at the sky? Yes. So the first way we move in the sky is as the Earth rotates. If you look at a star at dusk and then at dawn, the Earth is rotated by its diameter over the night. And so the object moves across the sky, but we're also seeing its angle in the sky vary. But the most common one that astronomers use is by observing a star now and then in 6 months from now. And the Earth has actually traveled to the other side of the sun in that 6 months and set up a baseline. And the baseline is 2 astronomical units, right? Each of the radius from the sun in 6 months. And so if you study a star now and 6 months from now, the stars that are closer to us will seem to jump, and the stars that are away. And here's where I share my screen. So let me just share my screen here.
Well, while you share your screen, I just wanted to answer Anita's question, which is how many sessions are there? And I'm afraid to tell you, Anita, we have no idea. We're just continuing on. We run sessions every other week for those of you who are new, and we're just continuing on as long as we can. Noting that today, a month and a half from now, we'll be at a year of doing these sessions. Anyway, back to parallax. Sorry.
Yeah. So this is a drawn not to scale diagram. So this basically says if you sit in your backyard and take a photo of the stars on one date, this is the picture you might get. And you see that this yellow star is relatively close and the rest are farther away. So that yellow star will sit compared to the other stars in the distance here. But then 6 months from now, if you take a photo of the same star, it's got a different set of stars. It's going to have the same stars beyond it, but it's going to appear to have jumped from the left to the right and back over the course of 6 months. And the amount of that jump will let us determine how far away the star is. Now in the sky, we use degrees, minutes, and seconds to measure the separation of objects in the sky. So 1 degree is about the width of your finger at arm's length. And then an arc minute will be 1/60th of that. Okay. And then an arc second will be 1/60th of each arc minute. So just to give you an idea, the moon is 30 arc minutes in diameter. And then each of those minutes has 60 seconds, arc seconds in it. So there's quite a few arc seconds across the moon's diameter.
If you remember back in December when Jupiter and Saturn got real close together, they were 6 arc minutes apart. If you manage to see that, then that gives you an idea of how tight that is.
Yeah, almost imperceptibly separated for the naked eye. Mm-hmm. Only when you magnified it were you able to really see them split apart. Now, the angle that the star jumps is really small typically. So the nearest star that we can see in Canada is Sirius, the star Sirius, and it actually is so far away that if this bottom of this triangle, so we're actually measuring the angle at the vertex of this triangle, but we actually cut the angle in half and make a right angle triangle. That lets us do the math formula a bit easier. But if the base of this triangle is 1 AU, for Sirius, the height of the triangle would be, let me see if I wrote this down. It's 547,000 times taller than the base of the triangle. So
Wow.
this diagram is really, really distorted view. So that's effectively, when you make a triangle that skinny, the angle at the very tip of the triangle is so tiny that it's a very difficult measurement to make. And of course, astronomers have to make those measurements through Earth's blurring atmosphere, and it can be difficult. And so astronomers, when they figured out that they could do this technique, actually took quite a while to work it out and get the measurements. I think the first star that was successfully measured parallax, its stellar parallax, was the star 61 Cygni, which is a kind of a summertime star. And it was done by Friedrich Bessel. Have you heard of the Bessel function?
No.
That's the curve that you use to grade marks.
Oh, bell curve.
The bell curve, yeah, that's a Bessel, kind of a Bessel function. He did it in 1838, but it took him several years of the back and forth of the orbit to get the measurement done. And I gave you a link to the paper where he published it. And it actually, I read a little bit of it. It's cool. It's sort of like, well, we're doing measurements and then Christmas came, so I took a break, and it's sort of a fun paper.
There's the paper. I know it looks like a questionable link, but I did just check and it's fine.
Yeah, it works. So as I said, the star Sirius is the closest star. So the closest star will have the biggest angle, even though it's small. And Sirius's angle is, let's see, I think I wrote it here. Maybe I didn't. Well, I wrote the angle for Proxima Centauri, which is the closest star to the sun. It's only visible in the southern hemisphere. It's 0.76 arc seconds, which is the equivalent to seeing a nickel situated 5.3 kilometers away.
That's insane.
So measuring the width of a nickel sitting 5.3 kilometers away.
That's insane.
And I gave you a link to an online calculator that you can type in the angle and it'll give you the distance to the star.
There we go. That's crazy. I have a hard time visualizing 5.3 kilometers in a horizontal aspect, but it's like, I know that the CN Tower is not 5 kilometers high, obviously, but I'm trying, like, just in a perspective of trying to get my brain around this, that, like, even seeing a nickel on the ground from the top of the CN Tower is impossible.
Yeah.
For humans.
Yeah. Well, if you have a good telescope, I mean, you need a big telescope and a very accurate picture. So in order to measure all the stars that we see in the nighttime sky, are neighbors inside our Milky Way galaxy. They're all at various distances from us. And in order to measure how far away they are, we're using these parallax techniques as one of the main ways. And it's tedious to do by astronomy, by hand, by astronomers taking photos. We've actually launched satellites that do the job. So we have a satellite mission called Hipparchus, named after a Greek astronomer. And its job was, I think it was between 1990 to 1993, for 4 or 5 years it went up, and it actually carefully measured the distances that stars shifted over the course of time. And it did about 100,000 stars. So if you're using Stellarium or an app like Sky Safari, and you see a faint star with the name HIP, then it's from that mission. It's been measured using that Hipparchus catalog mission.
Oh, cool.
Yeah. So they were able to measure stars with a precision of 1,000th of an arc second, and that gets them out to a few hundred parsecs. Oh, and by the way, I forgot to say what a parsec was. So if the angle you measure is 1 arc second, then the distance that star is a parsec.
Huh.
So a parsec is the height of this triangle where the base is of 1 AU.
Yeah.
And the angle at the peak is 1 arc second. And that's called a parallax second of arc angle. So they call it a parsec. And it actually translates to 3.26 light years.
Okay, so it's right.
It's about 3 to 1. So astronomers, both of those units of measurement are good for stellar distances. the diameter of the galaxy and so on. Astronomers tend to use parsecs instead of light years, but really it's like a 3-to-1 conversion. They like parsec because the parsec is actually a measured distance, whereas the light year is inferred, where we're assuming the object's distance from it, its apparent speed of light, travel, time, delay time, that kind of thing. So astronomers tend to talk parsecs, and outreach amateur astronomers, the media tend to use light years. It's
light year is easier to visualize.
Yeah, I think so.
Yeah,
I think so. Let's see. So the Hubble Space Telescope. So once you put your telescope outside the Earth's atmosphere, you can get much more precise measurements. So that's why Hipparchus was sent to orbit. The Hubble Space Telescope's been used for parallax measurements. They can get out to about 16,000 light years, or 5,000 parsecs. And then Hipparchus's successor is the spacecraft Gaia. And Gaia's mission, I think it's a European Space Agency mission. Its job is to study, 200 million stars. So a substantial percentage of the stars of our galaxy, down to 20 micro arcsecond precision. So that mission's going to go on till about 2024. It's currently underway. And that mission's cool. They've already started releasing the science from it. So it's been able to do things like tell us that the double star Albireo is a line of sight double and not an orbiting double, because we've got accurate measurements now for the individual double stars. So that's the kind of thing Gaia's going to be working on. Gaia's also measuring asteroids and comets and exoplanets and anything that can move slightly in the sky. So it's a pretty exciting mission. And one last thing we can do with parallax is that not only does the Earth orbit the sun, so we get that 2 astronomical units baseline to our triangle, but the sun is moving through the galaxy. The sun moves about 4 astronomical units per year with respect to the galaxy, the Milky Way galaxy. And so if you photograph distant stars now, and every year you wait, our whole solar system will have moved to a new position. So we have an increasingly enlarging baseline every year that we go back and review that star.
Sorry, you said it moves at 4 astronomical units per year?
Yeah, I think that's what I said it was. Okay. Yeah, about 4 AU a year.
I don't know why that seems so slow. It just seems so slow.
Well, space is big. But you don't want to, because at the same time, stars are jostling around inside the galaxy. So you want to get your parallax measurements done fairly quickly before they've had time to move to a new location. So there's all that as well.
Oh, true, yeah.
So bottom line is we can use radar ranging to get us through part of our solar system. And then we can use parallax to get us to the nearest few thousand light years away accurately. And then we have to come up with a new trick because we can't use that anymore. And so that's where we come into standard candles. So you may have heard the expression, I think somebody asked us a question about standard candles in one of our earlier sessions. So standard candles is the idea that if you know how bright something is, when you measure how bright it appears, you can infer how far away it must be. And a good example of that is, say, a motorcycle headlight. You have a pretty good sense of how bright a motorcycle headlight is. So if it looks faint, it must be far. And if it looks bright, it must be closer. Or a street light or something like that. I didn't say car headlights because then you can use the separation of the headlights.
Ooh, true.
Which is more like a parallax measurement. So the term standard candle was coined by Henrietta Swan Leavitt. She was one of the fantastic women astronomers that worked at the Harvard Observatory back in the late 1800s, early 1900s. And their work there was they were photographing the stars, star fields of the night sky, and they were not only measuring the star spectra, they were also measuring their location, they were measuring whether they varied in brightness, and they were measuring whether they changed in location. And she actually worked up or discovered that there was a kind of a star called a Cepheid variable star. And she actually found a number of this type of star based on its spectral fingerprint. So the spectra of the star is common if the star has a common composition in astrophysical structure, you can find multiple stars that have the same sort of fingerprint and know that they must be built the same, work the same. And she found that there is a certain type of star called we call it a Cepheid variable. I'll talk about that in a sec. That actually varied in brightness on a regular kind of a pulsing way. And she found those stars for which we knew the distance by parallax. And she plotted them up, and she found out that the brightness of the star was connected to this period of pulsation. And so she could figure out, she graphed it up and she figured out there was a period luminosity relationship. So she said, if a star pulsates at a certain number of days between brightness and brightening and dimming, then it's X brightness. But if it looks dimmer, it's far away. So she could relate what she knew how bright it should be and looked at how bright it appeared and was able to work out how far away those stars were. And they became a standard candle, a standard light. So it'd be like if you had a 100-watt bulb and you moved it from place to place and you knew it was 100 watts, but when it seemed bright, you knew it was close, and when it seemed dim, you knew it's far away. And you could even measure using a light meter how much dimmer it is and figure out how far away it is. Same technique.
So I'm just going to mention that this is in like the late early 1900s.
Yeah, 1912.
1912. It's wild that people could figure this out then. And like, oh my goodness, I'm constantly impressed by people who study astronomy professionally because there's so much math involved. Holy.
Yeah, the women, I've mentioned it before, the Glass Universe book by Dana Sobel is amazing because they did so much of the basics, the beginnings of our numerical astronomy and astrophysics work there, where they developed the stellar classification system, the OBAGKFM classification. They worked out variable stars and all of these things that people then built on that as they went.
That's crazy.
So let me talk
about.
Sent
just a heads up, I sent the link to that book that Chris just mentioned in the chat if anyone's interested in buying it.
So let me bring up Stellarium here, and I want to talk about this Cepheid, this word Cepheid. So the Cepheid variable comes because we found a star, and its name is Delta Cepheus. It's in the constellation of Cepheus. And it was the kind of first example of this kind of star. And then its name just got assigned as a type of star. So let me just bring up my Stellarium, and I'm going to show everybody where to find it because it's easy to see it. So here's the sky tonight at 8 o'clock. I'm just going to pause my time, and I'm going to swing around and face north. So there's Polaris, right? So Polaris is due north. You've got the Big Dipper sitting vertically just to the right, just to the right here in the northeast. And then opposite the Big Dipper is the constellation of Cepheus. And Cepheus looks a little bit like a box with a pointy hat, maybe a house with a pointy peaked roof, or a head with a pointy hat or something like that. And if you look, find this box and find the lower left corner. And I'm just going to zoom in, and you can see that there are 3 stars here. And the star in the corner is the brightest one. It's magnitude 3.35. And just a little bit off of that, I think it's, let me just see if I can measure it. So that's about a finger's width from that star is this star named Epsilon. It's a little dimmer. It's 4.15 magnitude. And up in the middle between them is Delta Cepheus. And that's the star that's the basis for the Cepheid variable stars. So this star, Delta Cephei, it varies in brightness by about a factor of 2 every 5 days and 9 hours. So it'll go bright, then it'll go dim, and then 5 days and 9 hours again, it'll be bright again. And when it's bright, it's as bright as this star, Zeta. And when it's dim, it's as dim as the star Epsilon. So any night you go out, you just need to find Cepheus, and you can instantly figure out where Delta Cephei is in its cycle.
Huh.
Yeah. So does it look as bright as this one, or does it look as bright as this one? And
Isn't
these
that
are
cool?
naked eye stars, or you could just throw your binoculars, and your binoculars would fit all three. So that's cool. So these Cepheid variable stars have been really amazing help to us, because when Henrietta Swan Leavitt was studying them, she was seeing them in the Magellanic Clouds. Those are the dwarf galaxies that are associated to the Milky Way. So she wasn't even looking at the ones in our Milky Way. She was looking at ones that were extragalactic. And that was giving her a sense of like she wasn't the one that put together the distance scale. She figured out the period luminosity relationship. And it was later on that we figured out how that could be used for calculating distances. So there's an astronomer named Harlow Shapley who worked at the Harvard Observatory. He found Cepheid variable stars scattered throughout our galaxy, and eventually, using the parallax as the distance ladder bootstrapping idea, started to figure out how big our Milky Way must be. And then we started finding these stars in other places. Now we're finding them in other galaxies. So as soon as we could start seeing them in the Andromeda galaxy, then Edwin Hubble used this principle to find Cepheid variable stars in the Andromeda galaxy, just by taking very detailed pictures of the Andromeda galaxy and noting the variable stars in it. He actually calculated that the Andromeda galaxy must be 929,000 light years away, which is wrong, but not a bad for a first guess. Because, you know, in his day, this is in the around 1930, in the early 1920s and 1930s, people thought the Andromeda galaxy was a nebula. They didn't know it was made of stars.
So figuring out that it was miles and miles away, well, thousands of light years away, was a really big deal. It meant that we weren't alone.
Yeah. Yeah. And as we'll come to know in a few minutes, it's actually 2.5 million light years away. Canadian connection, go ahead.
If there's a pause, Laurie Roche has a question, which is, why do they pulsate? Why do they change brightness? Do you know?
Yes, I do, in a way. So I'm not sure what the latest science is, but astronomers think that the outer envelope of the star hasn't achieved stability. So stars work by their gravity wants to collapse them, but their internal heat energy wants to expand them. And there's a balance. They're in a constant state of equilibrium. And that's why if the fusion in the star goes out, then the gravity takes over and collapses the star. So for whatever reason, in these stars, they haven't yet landed on an equilibrium. And one of the theories is that at some point in the cycle, the outer layers of the star prevent the energy from escaping. It's like a damming effect. And the dammed or contained energy then heats up the interior and causes it to expand. And that releases some of the heat, and then it relaxes again. So it's sort of this breathing, pulsating effect.
That's so cool.
Yeah, that's one theory. I'm not sure if that's the latest one.
And in all fairness, there are also lots of different types of variable stars, and some vary with these really
that's for another day.
Yeah.
But it's cool. It's cool that you can actually yourself go outside tonight on the next clear night and see Delta Cepheus and know how that star has influenced astronomy and the distance, the measuring the distance in the universe. Canadian connection. So Helen Hogg of the David Dunlap Observatory, her field of study was finding Cepheid variable stars in globular clusters. And she was able to help work out the fact that the globular clusters are in orbit around our galactic core. So they're outside of our galactic disk, but they're still buzzing around like bees around the core of our galaxy. And now, of course, we find globular clusters orbiting other galaxy cores like Andromeda, the Andromeda galaxy. Let's see. Okay, let's talk about supernovas. So Cepheid variables are a standard candle, and they're good for, as you can see, locally, but then also be able to use extragalactically if we can see them elsewhere. But another standard candle is a supernova. So there's something called a type 1 supernova. So when our sun eventually dies and reaches the end of its life, it will shrug off its outer core, its outer skin, and leave its core as a hot white dwarf star. And a white dwarf star is not fusing anymore. The fusion has stopped. It's just a hot ember that's cooling down over time. And in fact, the core is so dense that it's become what they call degenerate, that the gravity has squeezed the core to such a point that there's no space between the atoms. The atoms are all bumped against each other, and it's only the electron orbitals that are keeping it from collapsing further. So it's sort of in this sort of degenerate, hot degenerate condition. Now, if you get one of these stellar corpses, like our sun will make one of these one day, if it happens to be orbiting with a partner in a binary system, and it's close enough, its gravity, because it'll still have gravity, it still has mass, can actually pull matter off its partner. It's called accreting. And if enough of the matter gets robbed from the partner star, the white dwarf will grow in size. It'll grow in matter. And when it reaches a size that's astrophysically been calculated to be about 1.4 times the mass of our sun, there's so much mass and so much gravity that the interior of the white dwarf heats up, and it spontaneously triggers fusion to begin. But the white dwarf is mostly composed of oxygen and carbon by this point, after the sun's given off its shell. And once that 1.4 times the sun mass accumulates, it'll actually spontaneously, it's had too much, it's going to blow up, and it blows up in a supernova, and it spreads its matter through the universe. And what happens is that we know there's a rule that says when that supernova happens, it won't happen until enough mass is accumulated, and it won't last past that mass because it's the straw that broke the camel's back. So as soon as it hits that mass, it's supernova. And so we know how much matter is there. So we know how much energy is produced, E equals mc squared. So we know how bright it should be. And then we measure how bright it looks, and we can tell how far away it is.
So then is every supernova that happens should be the same brightness?
Of this type. There are different types of supernova.
Okay. Cool.
Yeah. If a star starts off massive, so this is a way of leveling up. So a star like our sun can never be a supernova. But if it has a partner that it can steal the mass from, then it can turn into one of these supernovas.
Cool.
Yeah, so it's called the Chandrasekhar limit, after Professor Chandrasekhar of India. And so we can see when these supernovas occur, they release so much light and energy that they'll outshine the whole galaxy for a brief time. So we can see them happening in other galaxies. And since we know how bright they should be, and we measure how bright they actually look, we can estimate how far away the galaxy is. That's another step in our ladder. So the Cepheid variable stars help us get to the near galaxies, but then supernovas are visible. These supernovas are visible over much greater distances, so we can actually tell that those galaxies and where they are.
Is now a good time to ask questions? Because we have several questions about the past few minutes.
Sure, let's go.
Okay. First off, Maria asks that could our sun pulsate? I guess that star pulsating also happens to our sun too. Does our sun pulse?
Our sun, I think it does vary somewhat, but it's not what we would consider a variable star. Yeah, it's a much more stable star. And there are implications about that for life evolving on the Earth. Would life have evolved on the Earth on a planet orbiting an unstable star or a variable star versus a steady state?
Because the temperature and the conditions would change so frequently, I guess, eh? And then Joanna asks, what size star ends in a supernova?
I think you have to be about 10 times bigger than the sun in order for it to become a supernova.
There's a really great, I also happen to know that Joanne is an educator herself, and there's a really great tool called Star in a Box. I'll see if I can find the link where you can plot what happens to a star, what temperature it is, what size it is over time, and what happens to it at its endpoint. So Joanne, I will try to find that and send it in the chat if I can find it. And that's
Now,
it for
go ahead.
That's it for the general questions that came from what we just talked about.
All right. So we're nearly done. I got one more step on our ladder, and then we'll get into actually pointing out objects to people to time travel out under the stars. So the top rung of the ladder is what we call cosmological redshifts. And that has to do with the expansion of the universe. So if a galaxy is extremely far away, almost to the point where we can't, resolve it, and it has a supernova, it becomes difficult to know. It becomes difficult to take those kind of measurements and accurately infer the brightness and some of the other factors. So the supernova standard candle gets us to about, I think, about 500 times farther than the Cepheid variable candle would do. But beyond that, we're up to some other tricks. And what we have is something called cosmological redshift. And what it is that if we know the wavelength of light being emitted by something, if it's taken a long time to travel to us, it's actually experienced the universe expansion during its traveling. And so by the time we detect it here on Earth, it's no longer the same wavelength it was when it was emitted. It's been stretched by the expansion of the universe and redshifted. So everybody knows that if you put sunlight to a prism, you get a spectrum. And if you really analyze one of those spectrums in detail, you can see that there's a fingerprint there. There are some colors that are brighter than the others, and there are some colors that are missing. So we have bright streaks, and we also have dark bands. And that's like a fingerprint that tells us about the object. It has to do with its composition and some of the other factors. So if we know that a packet of light or a light wave was emitted by a galaxy far away and traveled to us over many billions of light years. The universe is 13.72 billion light years old. During that time it's been traveling, it's been stretching, and the amount that it stretches is just proportional to how long it's been traveling, more or less. And so if you can actually make a formula that's the wavelength then when it was emitted, difference from the wavelength we detect, and then normalize that against the original one, and you get sort of a percentage. So it's like if it hasn't stretched at all, then that formula will give you an answer of 0. If it's stretched 100%, then it'd give you an answer of 2 or something like that. And so just to give you an idea, light that's not been redshifted at all is we call this parameter Z. This is a redshift parameter. Z equals 0 for something that's emitted now. The cosmic microwave background that surrounds us, it's the ultimate redshift. It's actually a Z equals 1089. And then objects that are closer than that, and that's basically going back to the Big Bang in terms of distance. Objects that are closer than that have redshifts or Z values that are less. So I think the farthest detected galaxy so far has a redshift of something like 11, Z equals 11. And what does that mean in distance? So Hubble, when he worked out the relationship between distance and speed, he worked out that the farther away something is, the faster it's receding from us. And there's actually a formula or a graph that you can plot. I think I've got it here. Let me just bring it up. I don't have it there. But so you can plot yourself on the graph and figure out how far away an object is heading away from us. And the slope of that graph is called Hubble's constant. And so if you do the math, it works out that you can do Z equals Hubble's constant, where is it here, times distance. Hubble's constant times distance divided by the speed of light gives you the Z. And if you flip the math around, you can solve for distance. So we can find out how far away things are based on the redshift of their light. So that's the top of our ladder, distance ladder.
Oof. Okay, so I remember almost none of the math on that, but
It's
I
exotic.
trust you that you know what you're doing.
Yeah, it's exact. It's not important. So let's get out to brass tack. Let's take people outside. So I'm just going to get I'm just going to get you and I off my screen.
Well, while you set that up, I'll just quickly answer Atul Dave's question, which is it true that the sunlight is actually blue-green? This is actually a much longer and complicated question that I probably should have tried to tackle in this period while Chris is getting us set up. But essentially, every star emits light in a specific range. The sun emits it over the entire visible light spectrum range and in ultraviolet and infrared as well. It peaks at the sort of like blue-green wavelengths, but the way that stars work, they can never really be green because they're always emitting that spectrum of light. So it usually goes, and when you're thinking about colors of stars, it goes from like blue to white to yellow to red, et cetera, et cetera. And so our sun looks kind of like what, white yellowish? Hey, Chris?
Yeah, each color has a temperature. And so the sun's temperature, the sun's visible surface called the photosphere, has a temperature of about 5,800 degrees Kelvin, which corresponds in the spectrum to about yellow, close to yellow. But we see a number of colors all arriving at once, so they combine to give us a white effect.
Yeah.
Was that answering the question? What was the question?
I think so. Yeah, these are the big tough questions. There are no green stars, technically speaking, nor are there purple stars. They're either blue, white, yellow, etc.
Yeah, it's partly because the stars emitting the whole family of colors towards us, and we see them all as a combined group. So we don't really see the individual shades of color, but we do see senses of it. So we can get towards the blue or towards the red, but the ones in the middle are all combined together. So yellow and green are really kind of in the same family.
Mm-hmm.
All right. So imagine you're heading outside tonight on a clear night. It's not clear where I am, but hopefully it's clear where you are. Now, what's cool about this this exercise is that we do have viewers that are in places where the sky is amazing. So let's challenge them on a couple.
Yeah, there are so many folks from all over the place here.
So I already mentioned that. The room around you, you're seeing in the past. You're seeing that 3 nanoseconds delayed for each meter away something is from you. Maybe your significant other or your parents or something like that. You're detecting them in the very, very microscopically past.
Tiny bit in the past.
If you look up and you see a meteor or the aurora borealis shining overhead, that's occurring about 100 kilometers above your head. And that's about 0.3 milliseconds in the past. So you're already traveling. Yeah, that's almost detectable by, stopwatches, things like that.
Yeah.
The International Space Station. So let's talk about the International Space Station. So satellites are farther away. I'm just going to bring up my bookmarks here in a second. So the International Space Station is 425 kilometers above the ground. And that works out to 1.3 millilight seconds away. It's easier to use kilometers, right?
Yeah.
Yeah. But it's basically 1.3 thousandths of a light second delay.
That's hilarious. This is where it gets very silly. And if you're a student and teachers ever tell you to specify your units, this is why, because technically you could measure some short distances in millilight seconds, but I don't think your teachers want you doing that.
Yeah. Now, just for curiosity, for those that might be viewing from the Greater Toronto area, there's a great pass of the International Space Station on Thursday. Let me see if I can open up this bookmark.
I just sent the link out in the chat for those who are interested. I'll put it in the YouTube video as well. Oh, also, just a heads up, someone on YouTube is watching from Switzerland, so that's very exciting.
Okay, thought I could do this. It's not letting me do it. Go to bookmark. Let's try that. No, doesn't want to work. Anyway, that's fine.
Do you want me to bring it up? I have it up on my screen if you want.
No, I mean, I can do it manually. I was hoping to do it. I was hoping to be tricky and do it with a bookmark in here. So let me just bring up this and show you the International Space Station. Let's see if I can find it. There it is. So there it is. So there's the International Space Station. Oh, that's not the right one. I'll just use my search tool here. There we go. And if I play this in real time, you can see it drifting across the sky. So when we're seeing the International Space Station, you're seeing it slightly in the past. Same with all the other satellites that you'll see in the night sky. There's another little one there. They're all working at about 1.3 millilight seconds away from you. Now, tonight, the moon will rise very, very late. Let's see if I can find the moon here. And when you look at the moon, you're actually seeing the moon, as we said, 1.2 light seconds in the past. That's why if you're communicating with astronauts when they're on the moon, there's a bit of a delay when you're talking to them, a slight delay. But in terms of the solar system neighborhood, the things that we're used to seeing, the planets and so on, Mercury, so tonight, go back to tonight, if you have a clear western sky at about 6 p.m., you can see if you can spot Mercury. So when you see Mercury, it's actually going to be, where are we here, 107 million kilometers away, which is a bit clumsy, or 0.7 astronomical units away, or 5 minutes and 59 light seconds. Five light minutes, almost 6 light minutes away, because it's out there near the sun. Later in the evening, if you look up and see Mars, and stellarium actually gives you the light times here, see, light time, 10 minutes and 4.6 seconds away. That's how long the light from Mars has been traveling. And don't forget that Mars is shining by reflected sunlight, so the light from the sun had to go out to Mars, reflect off of it, and come back to Earth. So the distance of Mars from the sun is probably 10 or 11 light minutes, and then it's that extra. So you're seeing even older sunlight when you do it that way. If you can see the Milky Way, so the sort of glow of the Milky Way, those stars are so far away that we can't see them as individual stars. We're actually looking towards not the core, more like the outer rim of our Milky Way galaxy. So it could be up to, say, 50,000 light years away when you're seeing the glow of the Milky Way galaxy. So that light's been traveling for 50,000 years to get to your eye.
That's crazy.
Yeah. So, but let's start a little bit closer to home. So Sirius, the bright star Sirius, is the brightest star in the nighttime sky. It's the closest star really that we can see from Canada. Proxima Centauri we don't see from Canada. So it's 8.66 light years away. That's 82 trillion kilometers, or 93 million years of driving at highway speeds to get there.
Oh.
Now, the light that we see tonight from Sirius left Sirius on June the 6th, 2012. So I wonder if we have any viewers that were born around then.
How old would they be? Would they be 8?
8.66 years old.
8 point, yeah. Okay, let us know if you're 8.6, whatever, 66? 8.66 years old? Yeah.
So you can actually find your birthday star. You can find a star that sent its light when you were being born. And there's a website, Jenna can post the link to the Birthday Stars website. And if somebody wants to volunteer their birthday, we could do this. The problem is if you do it for an older person, then you're looking at a farther away, dimmer star. But if you can find somebody who's relatively young.
I can volunteer my birth year if needed, but I know that
you don't need the day.
I was born in 1992.
Okay, let's see.
I also know that my boss is in the chat, and if you don't know the executive director yet, Phil really enjoys his birthday. So Phil, if you want to, I don't know if you want to go as far as to share your birth year, but it's an option.
Well, the problem is that, again, if we pick somebody that's middle-aged, then the stars aren't going to be very bright. So when you do this, I'll just bring up and share my screen here. So when you plug in your birthday and you say, find my birthday, it gives you a list of stars. And you can see that these aren't very well-known stars, but it'll give you the distance in light years. And then it gives you the brightness and magnitude. And the smaller this number, the brighter it is. and it gives you the constellation and so on and the other names for it. And the offset is how many days its distance is off from the date you put in. So we're only off by 2 days here from January 1st, 1992 for this star. And you can actually type these names into Stellarium, but let's say, let me pick something. Let's pick a millennial. Let's go with.
Oh, we have a date here from Gord saying October 12th, 2009. How about that?
Oh, great. Okay.
Not a
October
millennial.
12th.
Well, technically not a millennial. Someone more interesting and younger and livelier than a millennial.
October 12th, 2009.
Someone who knows how to use TikTok, probably.
All right, look at that. Procyon.
Hey, that's awesome.
A winner.
Oh, that's a good one.
A winner. All right. So you're off by a few days, but that's a nice bright star. And you know what? There's 61 Cygni. That's the stellar parallax one we talked about.
Gord,
So
did you know this
that's a
date was
winner.
going to be okay? Your grandson's a lucky person.
Yeah, there we go. All right. So yeah, Sirius, let's go through. So generally speaking, the bright stars you see in the night sky are the nearest ones. So as we said, Sirius is the closest one. Procyon, here's Procyon up here. So Procyon is part of the Canis Minor, the little dog. It's 11.46 light years away. So you're seeing 11.46 years ago. Pollux, 33.78, almost 34 years. Capella, at the top of the winter hexagon up here. Capella is 42.8, almost 43 years ago.
Okay.
Castor is 51.5. Aldebaran in Taurus, 66.6 years.
Hey.
Swing around and look at the Dipper. Mizar, where the handle bends in the Big Dipper. That's 78.16 years. And by the way, most of the stars of the Big Dipper are all approximately 80 light years away from us because they're related to one another. The only two that aren't are Dubhe, which is farther. It's 123, and Alcade, which is 104.
They're all kind of moving around together too, eh?
Yeah, they're traveling together. That's why if you use Stellarium to preview the sky many thousands of years from now, the Big Dipper doesn't vary in shape much because all the stars are traveling as a group.
I have somewhere back in my save tabs, I have a video of how the Big Dipper has changed over the past 100,000 years. I'll see if I can find it and share it.
Yeah, you can do that. So that's Mizar. Let's see, Mirach in Andromeda. So we have Mirach here. Here's the Andromeda galaxy. If anybody's, we'll come back to that in a minute. But Mirach is 197 light years. Almach is 354. So now we're going in the past 354 years. And just let me go back to the north and look at Polaris. Polaris is 432 years. So that's getting into the time of Galileo.
Oh, that's very cool.
Right? Betelgeuse. So one of everybody's favorite constellations, Orion. So Betelgeuse is 548 light years away. Rigel. Now Rigel and Betelgeuse look the same brightness roughly, but Rigel is 862. So it's quite a bit farther away. That's because Rigel is more luminous and it's giving off more light than Betelgeuse is. And I've got two more. One here is the middle star of Orion's belt is Alnilam. It's 1,976 light years away.
Ooh.
So that's, just in the, first zero century, the year 70 AD or something like that. We all know what the world was like then. And then back to our friend Cepheus. So again, swing around and look north. Find Polaris. Now remember, this is the little group with Delta Cephei. This is Delta right here, this little triangle.
Oh yeah.
And if you find the box and find the red tinted star that's below and between the middle row, the middle edge of the box, that's the Garnet star, Mu Cephei. It's a giant old star. It's nearly 6,000 light years away, and it's a naked eye star.
That's so cool.
So you're seeing light that's been traveling for nearly 6,000 years.
That's crazy.
It's great in binoculars and a telescope. It's a very red colored star. So that's called Mu Cephei, or the garnet star. All right, heading back to the question.
I was just going to say, on the note of birthday stars, Anne pointed this out, that that she would try it with her grandchildren. And this is a great way to, or it's a great way to engage younger people and people in general. If you want to drag them out observing with you, go and drag them out with the star that's, you know, as far away from us as they would be if they were born and launched into space at light speed.
Yeah, I mean, you could make it an exercise that you have to figure out your birthday star and be able to locate it.
Yeah.
Get your star finder and, you know, circle that star in your star finder, or put a dot where the star finder is. Personalize it like that. Okay, now deep sky objects. So deep sky objects are things that aren't individual stars. They're clusters and nebulas and galaxies and so on. And the closest deep sky object that you're going to see out on the night sky is the triangular face of Taurus the Bull, except for Aldebaran, which we already talked about as being only, what did we say, 67 light years away. But the other stars that make the V shape of Orion, of Taurus's face, we call these the Hyades star cluster. It's 150 light years away. And again, they're all siblings of one another. They're all traveling as a group. So what's the nearest open star cluster to the sun? The biggest, that's why it's so big in the sky. But don't forget the Pleiades. So you've got the Pleiades, or seven sisters, sitting up above it. The Pleiades are also about 440 light years away. So again, that's Galileo's time, right? So Galileo was observing the moons of Jupiter in 1610, and that's 410 years ago, 411 years ago, whenever it was. So we're talking about light that's been traveling since Galileo was using his telescope in those times. Back to Orion. So grab your binoculars or your telescope and point it at the Orion sword and look for the nebula. The Orion Nebula. The Orion Nebula is quite a big object. It's 1,340 light years away from us. So it's in the next door arm of the Milky Way galaxy. The galaxy has these arms that wrap around. It's in the next door arm. When the light left the the Orion Nebula, it was around the time of Islam was being born on Earth, that religion of Islam. It was the Tang dynasty in China, and there were about 208 million humans living on Earth around that time when that light left the Orion Nebula.
That's wild.
Yeah. Swinging around to the north again. So there's Polaris. Look for Cassiopeia. So this is north, and this is straight overhead, this little Z. All right. There's Cassiopeia, and in between Cassiopeia's W and the zenith, look for two smudges of light. Use your binoculars. This is called the double cluster. The double cluster is 6,800 light years away. So that was the post-Neolithic era on Earth. We were getting early pottery being created by humans on Earth. There might have been about 40 million people living on Earth at that time. Then we've got, then we've got, as I said before, we've got the Milky Way, the winter Milky Way. It kind of runs up through Taurus here. I can actually make it a little brighter if I just turn off the sky for a minute. There you can see the Milky Way a little better. So when you're seeing that Milky Way, you're probably looking about 50,000 light years away. So that light's been traveling for 50,000 years. That's the upper Paleolithic era. Humans were making stone tools. The Neanderthals were still around. There might have been 1 million people on Earth at that time when that light left the edge of the galaxy.
You can almost guarantee that 0 of those 1 million people were thinking about this.
And here's my favorite thing to talk about in terms of the Andromeda galaxy. So here's where we're going to bring in the people who have pristine skies. So the Andromeda galaxy is sitting here in the western sky. Remember, here's the zenith. So zenith is straight up. So it's high in the western sky in early evening. Here's about 7 p.m. And I'll just zoom in on the Andromeda Galaxy. So the Andromeda Galaxy, using Cepheid variables and the other methods we've used, is about 2.6 million light years away. So the light has been traveling all that time. And at that time on Earth was the first Homo habilis beings on the Earth. It was the ice ages in part of the world. If there are astronomers on planets orbiting stars, the Andromeda Galaxy, they're seeing the light that left here 2.6 million years ago. So they're seeing us in the past. So it's all relative, depending on where you're observing from. Everything else is in the past for you. And I just think that's amazing.
That is so cool.
Now, this for most people will be the farthest away thing your human eyeballs can see. 2.6 million light years.
Those are some old photons.
Yeah. If you've got good eyes, you can swing around and look at this patch of the sky. And this is located, I'll just do a little measure here. This is about 1.5 fists diameter to the left of the Andromeda Galaxy is the Triangulum Galaxy. The Triangulum is this funny triangle-shaped constellation. The Triangulum Galaxy, you can see this in binoculars, no problem, if you have a dark sky. It's about 2.8 million light years away. And a lot of people have claimed to be able to see that with their unaided eyes, so they're getting even better. But wait, if you've got really good eyes and really good skies, swing around to the north. This is not the best time of year to do this, but just above the bowl of the Big Dipper, let's see if I can find this guy here. I'll just cheat and I'll bring up the pictures here. Here we go.
I love that there's a Fabergé egg galaxy. Sorry, I just saw that pop up for a second. I think that's a hilarious name.
Yeah.
For a galaxy.
So there's the bowl of the Big Dipper. Go up from the bottom of the bowl up where the handle is, through the rim, and double it, and look here. And there's a pair of galaxies called Messier 81 and Messier 82. And some people claim to be able to see Messier 81 with unaided eyes.
Really?
And if you can, you're looking 11.8 million years into the past.
Oh, man.
So that would be the Miocene era on Earth, the very first hominids walking the face of the Earth.
If anyone has seen it, or if anyone thinks that they've seen it with the naked eye, comment in the chat, please, because I would like to commend you. And also, like, that's just crazy.
Yeah. You can see that the magnitude is 6.94. So it's a relatively high surface brightness galaxy. The stars are packed into such a small area of the sky that the accumulated brightness allows us to be seen. It's definitely binoculars, but if you can see it with your unaided eyes, then you're a winner. You're a real winner.
There's an astronomer. Oh no, I can't remember where they're from or any details about it. Wow, why did I say anything? But they're visually impaired and they can't see well in light. The light is too bright, but at nighttime they can see so much more because all of a sudden the lights are turned down and they can see all this detail and all the stars out there. Anyway, it's really cool. I'll see if I can find an article.
So the best time to see a galaxy like that is when it's highest in the sky. You can see that right now it's relatively low in the sky. Here's the zenith and here's where M81 is. But at different times of the year, the Big Dipper rides high in the sky. Let's see if we go. So if you're out late at night, it'll be highest at night around midnight. So midnight tonight. So that would be the time to take a look for that. But let's stick with the evening sky. All right, so now that's naked eye. That's about the limit I think anybody can expect to see back in time. So from micro light seconds for satellites to maybe 12 million years ago with M81. Let's say you use binoculars or telescopes now. So this gets pretty easy. So binoculars, telescopes, you've got Uranus, Uranus is up here near Mars. It's, let's see, almost 3 light hours away. If you focus your binoculars in the space to the left of Orion's belt on a dark night, look for this big fuzzy patch. You might even, I don't know if you get the pink color, but you'll definitely see the fuzzy patch. That's the Rosette Nebula. The Rosette Nebula is a real winter showpiece. You really want to take a look if you've got binoculars or a telescope of any size. It's, let's see, it's 5,400 light years away. And then if you look up into where Capella is, inside Capella, if you just scan with binoculars, you're going to see a number of bright patches of stars. These are open clusters. And these ones are all about between 4,200 and 4,500 light years away. And finally, we're getting to the limit of even backyard telescopes. Go back to the north for a second here. Down near the tip of the handle of the dipper, let me bring this up into closer to midnight. If you scan with your binoculars, find the tip of the handle, scan to the left, you can see there's a little fuzzy patch here. That's the Pinwheel Galaxy, Messier 101. That's pretty easy binoculars. That's 21 million light years away. And then if you go the other way, so sort of kind of in the opposite direction about here, that's M51, the Whirlpool Galaxy, and it's 23 million light years away. And then there are other things we can talk about. The last thing I want to mention is a quasar. So a quasar is an active, basically it's a feeding black hole, we think. So as the black hole is swallowing up material, it's accelerating that material and it's generating a lot of radiation, and we get these incredibly bright objects that are at vast distances from the Earth. And there's one called a quasar named 3C, let's see, it's here, 3C273. I'm going to go to it. And it doesn't look like anything but a dot, but if you have a really big telescope, you can find this dot of light using your star patterns around it. It is actually about 2.44 billion light years away.
Whoa.
And it's one of the farthest away objects that an amateur astronomer can see in an amateur telescope. Quasar 3C273.
That's crazy. How bright is it, Chris?
Let's see the magnitude. I don't remember the magnitude. Let me just see if I can find it. 3C273 magnitude.
I'll see if I can find it too. Oh,
10. Looks like it's 10 point.
Might be 12.9.
Yeah, it's within reach of telescopes.
That's cool.
I have it shown here in Wikipedia. In one site is 10.25, which is certainly. But it is. I mean, it's just a dot, so it's harder to figure out. You really need to match your star patterns to figure out which one is which.
That's very cool, though.
So that's your travel through time. A couple of final thoughts. And we're going to do one of these days, we're going to do a session on misconceptions in astronomy. And one of them is that I've heard people say, don't wish upon a star because it's already dead. Have you heard that?
Dreams. Yeah, I've heard that.
People think that the stars are so far away that they've already died. No. The stars that we're seeing in the sky, they're all, the farthest one we're seeing with our naked eye is a few thousand light years away. Stars live for millions of years, in some cases, billions of years. They're still there. Go ahead and wish away.
The odds are high that they're still there.
Yeah. Even the galaxies that are millions of light years away are still there.
Yeah. I mean, what are they going to do? They're not going anywhere.
Well, the stars, the brighter stars in the sky tend to be short-lived. So the Sirius and, Orion's belt, they live for millions of years, not very long. So come back, our descendants will see our sky differently, the winter sky differently when when they fizzle out or supernova or whatever they do. But
Yeah.
now in terms of when you look up at the sky, you're looking into the past, and the light that's coming will still come for generations to come. And I think that's a cool note to finish on.
So now we have a question that about in this exact same category from Joanne. If a star goes supernova today, would it take us many years to see it then?
Yeah, obviously. So it's depending, if a star is X light years away, then the explosion will take that many years to arrive.
And there's some
So
really
a
cool
year
stuff.
ago when Betelgeuse dimmed, is that what you're going to say?
No, you go ahead. We can talk about, you talk about Betelgeuse. I was going to talk about neutrinos.
Yeah, so about a year ago, a little more than a year ago, Betelgeuse suddenly dimmed, and people thought maybe it was getting ready to explode. And because it's close to 600 light years away, the explosion would have happened 600 years ago if we just are now seeing it. It turned out that it re-brightened, and that may have just been some opaque dust that was orbiting the star and blocking its light. But yeah.
My hopes were high that it was going to go supernova, because I don't know, I'd love to see one. Anyway, what I was going to mention was that in neutrino labs, there are these little tiny subatomic particles called neutrinos discovered relatively recently-ish. Very, very small mass, but they do still have one. And I believe the way it works is that before supernova, like well before supernova, neutrinos are released. So there's like a little burst of these neutrinos that go out in every direction. And neutrino observatories, like the one in Sudbury, and there are several, there's one in Antarctica, there's one in Japan, they'll detect which way the neutrinos are coming from, and then we'll be able to send out a quick, hey, everybody point your telescopes at this spot message. And then everyone will turn around and point their scopes to look for that supernova from miles, many years, light years.
Yeah, the reason that happens is that when a supernova is happening, it's there's an intense increase in gravity, increase in density, increase in fusion, and neutrinos are produced by stellar fusion. But neutrinos don't interact with regular matter very much at all. So they can flee, they're fleeing the explosion before the rest of the guts of the star explode. So that's why we get them early, because they've had a chance to escape immediately. They're not bumping into mass inside the collapsing star. It's
very, very cool. And this is not to do with supernovas, but the Sudbury Neutrino Observatory, the SNO Lab, one of the professors who does research there, Arthur MacDonald, won the Nobel Prize several years ago, I think 2017.
Yeah, I did. I went on a tour of the SNO Lab 10 or 12 years ago. And the gentleman that led my group was this humble man named Art. And
no way. That's awesome.
Him.
That's so cool. What a cool experience to have. Oh man. If you can ever get a tour of SNO Lab, or if you ever want to study like astroparticle physics, that's a very cool place to do it. It's 2 kilometers down in a mine and then 2 kilometers over to like this perfectly clean underground bubble of experiments. Very, very cool.
Yeah. First you dress up as a miner, and then you shower down and you dress up as a scientist.
Yeah, it's what, because if you bring dust in, then like it messes up the entire experiment, which is pretty hard not to do when it's in an active mine. But regardless, very cool. I recommend. There are a couple questions. One from Atul Dave. I think probably what you meant when you said what is a neutron. I think you probably meant what is a neutron star, which is a star that has collapsed, but it's not so massive that it turns into a black hole. Instead of turning into a black hole, it'll turn into a very dense star.
Yeah. So stars are made out of matter. Matter is atoms. Atoms are made out of protons and neutrons and electrons. But most of the time, there's gaps between the atoms. I mean, they click together to make molecules and so on. If you squeeze matter down to the point where there's no longer any space between the atoms, then you get the white dwarf I talked about, the degenerate matter. But there's still space inside the atoms between the nucleus and the atom, the atomic orbitals. But if you keep going and squeeze even those, then the space between the atoms, the space inside the atoms gets shrunk. The electrons and the electrons and the protons fuse to turn into neutrons, and you end up with a hunk of neutrons with no empty space in there at all. And that's what a neutron star is.
If you scooped up a
Generate matter.
teaspoon of material from a neutron star, is one of my favorite ones, it would weigh about the same amount as Mount Everest here on Earth. Something like that.
That little? Maybe
yeah, that
more.
little. I think that little weighs the same as mass. It's some insane mass, like that you could never conceive of. So very, very cool. And lastly, this is a question from one of our younger viewers, I believe, because Damon, I've seen you in here before. Damon asks, how much mass does a black hole have? And this is like a giant question to answer on, because the answer is it depends.
Well, black holes can come in many different sizes. Their size depends on how massive was the object that turned into a black hole, and number two is you can grow a black hole by accreting or absorbing more mass, and you can also merge black holes. And so if you merge two black holes, they'll become a double-sized black hole, double the original size.
It's kind of like saying, how much does sand weigh? Or like, how much does the sand on a beach weigh? It's like, it very much depends on the size of the beach. It depends on how much there's involved, how much you're talking about.
Yeah. So the sizes of black holes, because black holes are made by a process that began as a real object, then black holes tend to come in families of sizes. So the black hole that is made by a big star will be the same mass as that star, roughly. And so you'll just get black holes that have the same mass as a star would. But in terms of today's topic in black holes, remember that all of this that I've been talking about today has to do with being able to see the object, either see the object move in space or see its light. And since black holes are invisible and give off no light, we cannot use these techniques to measure the distance to black holes. But what we can do is find black holes that have partners that we can see. And that's how we tell how far away they are. So if we see a black hole tugging around a star, we can use spectrum or star's parallax to figure out how far away that star is, and therefore its partner, the black hole. So
that's one of the coolest things. There was one last question for what is the smallest a black hole can be, and I just Googled, and Google says that the smallest is 6.3 solar masses. That is from Scientific American, so I trust them. So that is as small as a black hole can be in theory.
Okay.
But that's as far as we've seen so far, right? Like, who knows?
Yeah, the idea is that if you squeeze something enough, it could be a black hole, but how do you do that squeezing? And that's the process, that's the difficult part.
Yeah.
So a naturally occurring black hole is generally produced by a star that collapsed, and so that we get a certain size from that. Maybe black holes were formed during the Big Bang. Maybe black holes there's a whole bunch of little teeny black holes scattered around, and they're part of what dark matter is. We don't know. Exactly.
It's hard to say what is the absolute on this stuff, because we're talking about the absolute based on what we know right now. And, I don't know how long it's been, but we haven't, in the grand scale of human lifespans, we haven't known about black holes for that long. So we can't say that for sure we know that the smallest is 6.3 solar masses. Maybe we're just not seeing the smaller ones. And I think that wraps it up.
Cool.
Yay.
Good session.
Thanks everyone for coming. We had a good time. Nice to see you all. We will be on again February 16th, and I forgot to check what our topic is.
The moon.
The moon, duh. Yeah, we're talking about the moon. We haven't actually done a session about observing the moon, so we're going to do an observing the moon session specifically. So we'll see you all then. Bring your binoculars and your lunar goodness. And that'll be in 2 more weeks.
Excellent.
Thank you, Chris, for all of your brains today.
My pleasure. Thank you all for your interesting questions.
It was fun to see everybody again. Take care, everybody. We'll see you next time. Keep looking up.
Keep looking
I stole
up.
your phrase. Sorry. Clear
That's
sky.
okay.